Yeah. Thank you for your introduction and thanks for invitation. It's my great honor to speak here. Okay, so in a recent work of Liu Pan on the locally analytic vectors of the completed cohomology of model curves, Liu Pan considered such setting. He considered a one-dimensional smooth affine-dialectic space, and he considered a prologoidal perfectoid cover. This is perfectoid affine-dialectic space. And he assumed that this tower has Galois group, which is a compact p-adic analytic group. So p-adic analytic group is another name of p-adic Lie group. And Liu Pan constructed a canonical element, theta. That's in B QP times the Lie algebra of G. This canonical element is a geometric analog of the Sen operator defined over local fields by Sen. And one of Pan's results is that this element theta will annihilate the G locally analytic vectors in B. So we want to understand Liu Pan's result from the perspective of the classical Sen theory. I mean, the Sen operators defined over local fields developed by Sen-Brinon. And we will, in our work, we will generalize the Sen operators over local field to Sen operators over p-adic varieties with semi-stable charts. And then we will discuss its relation with Lie algebras. And finally, we give the generalization of that the geometric Sen operators will annihilate the locally analytic vectors in higher dimension. Okay, our strategy for generalize the definition of Sen operators in the relative situation is to glue the Sen operators defined over local fields. So let me first to recall Sen-Brinon's construction for Sen operators over local fields. So let K be a discrete, complete discrete evaluation field with characteristic 0p and with imperfect residue field K. But I assume that it admits a finite basis. In this setting, we can choose T1 to TD, like in OK, a system of liftings of P basis of K. This can be regarded as a system of coordinates. And then we consider a tower. From K, we first consider the cyclotomic extension, I mean, adding all the roots of unities, Tn's roots of unities. And then because our residue field is imperfect, we need to do a little furthermore, which I adjoin the power roots of these coordinates. Okay? And then I name some Galois group. Of course, we fix the algebraic closure first. And I name some Galois group. This is called by G, and this is gamma, this is delta, and this is sigma. Okay. Our main objects are finite-dimensional continuous k-bar hat semi-linear representation W of the absolute Galois group. And I denoted by W an object of this category. So to define the Sen operator, the key is the descent theorem of such category. So we can consider the base change functor from gamma with coefficient in k infinity infinity. And if we have an object v infinity here, I maps to the base change. Sen and Brinon proves that this is the equivalence of category by almost the Galois descent and the decompletion. So I mean, for any W, you can find such a V infinity here, such that its base change is equal to W. I remark that one can descend further to some delta analytic. I will define this later. That's analytic gamma representation, but with coefficient in just the cyclotomic tower. This is also equivalence proved by Tsuji in his p-adic Simpson correspondence. So one can descend this to V. So by delta analytic, I mean in this setting, we have more explicit version. So for any element in delta and any element in V, so this action can be written as an exponential of some endomorphism phi tau, I will define later, times V. And this phi tau is the infinitesimal action tau to the A times V minus V. So this is the infinitesimal action. And this is the definition of delta analytic. Okay. So notice that here, because we have such a setting, and we know that ZP is an open subgroup of sigma, and we have ZPD is an open subgroup of delta, so that here we have a semi-direct product which identify with the open subgroup of gamma. So that in particular, we know that the Lie algebra of delta is equal to the Lie algebra of ZP semi-product with ZPD. So one can take out the standard basis. This is the standard basis. Now I consider the infinitesimal action of delta 0 of V, and I extend scalars to k bar hat. So this will be an endomorphism k bar hat of W. And of course we have the others phi and so this is called the arithmetic Sen operator. And these three operators are called the geometric Sen operators. So in fact, you see that the Lie algebra of gamma acts by infinitesimal action on V, and extend by scalars. We know that Lie algebra acts on W. But this action is non-canonical because we have chosen the liftings of a P basis. But anyway, we get such a action. So in fact, these Sen operators have a lot of properties. For example, these Sen operators will determine the isomorphism class of representation of G on W. And especially we are interested in the following theorem because we want to discuss its relation with the algebra. So this theorem is proved by Sen in the perfect residue field case and generalized by Ohkubo in the imperfect residue field case. So let's say that I be the inertial subgroup of G. And let's consider if the representation is coming from a finite-dimensional continuous representation of G with coefficients in QP. And of course, we need to extend by scalars in K bar hat so that we can define Sen operators. The conclusion is that then I consider the Lie algebra of rho I mean the actions of I, it can be regarded as a QP subspace of S. This is the smallest QP subspace. Such that if we consider the Sen operators of W, it will contain in the base change of this subspace. As a vector space of in the morphism of W. In other words, it means that if your representation coming from QP, then the Sen operators essentially capture the action of inertial subgroup. So in our work, we would like to generalize the construction of Sen operators to the relative situation, and especially we would like to generalize this theorem. But you see that the Sen operators are defined in a non-canonical way because we have chosen the liftings of p basis. But in a relative situation, you have a lot of height 1 primes. It's not clear whether we can choose a system of coordinates of the p-adic variety such that at each height 1 prime, you will get a lifting of p basis. So the first question is that if we can define Sen operators in a canonical way, or if we can find a canonical Lie algebra action on W, once we fix the basis, then we will get those non-canonical Sen operators. The answer is yes, because so I will write it here because I want to keep it for a while. So there is a canonical construction of Sen operators. We need to use the Faltings extension of OK. So this is a canonical exact sequence. We have K bar hat twisted by 1 Tate twist, and we have a Faltings extension called EOK. Doing math, and we have the differentials. The differential of OK over ZP, and we get the p-adic completion. So how this Faltings extension is defined? It is defined by it is a Tate module. It is defined by the inverse limit of omega OK over OK, OK bar over OK. In fact, it is a finite dimensional. It is finite dimensional of 1 plus D, and it admits a basis. So if you take the liftings of the p basis, and we consider this log differential, and it forms an inverse system here, and we consider I bigger than 0, less than n, where I simply denote T0 by our pnth root of unity. So in fact, it looks very large, but in fact, it is finite dimensional. This forms a k bar hat basis. So we can consider taking its dual and take a Tate twist. We can consider the dual version of that. We have home OK. We have the complete differential twisted by -1. We have k bar hat. We have J dual. We have our dual of Faltings extension. And finally, we have this linear form. Okay. So, in fact, there is a canonical Lie algebra structure on that. So, in fact, this is a canonical Lie algebra structure. The Lie algebra structure is induced by this canonical linear form. So, it defines explicitly by this. The Lie brackets of two elements here. We have iota F1. This is an element in k bar hat times F2 minus iota F2 times F1. So one can check easily that it forms a Lie algebra. And explicitly, if we take the dual basis of such a basis, in here I denoted by T0 star, which is a dual basis here, then you can check that the Lie bracket is just T0 x others by this, and for ij bigger than 0, they commute for any ij bigger than 1 less than n d. Okay. Yeah, T0. Yeah. Okay. So this canonical Lie algebra will replace this non-canonical Lie algebra. So we can give our canonical construction of Sen operators. There is a theorem. So for any finite dimensional representation of G with coefficient in k bar hat, there is a canonical Lie algebra action. I call it by Sen, restricted to W, from our canonical Lie algebra to the endomorphism of W. This is a homomorphism of Lie algebras, which is G equivariant. I mean, G acts naturally on our Faltings extension, and G acts adjointly on this endomorphism. And also it is functorial in W. It can be defined explicitly. So we forget about the lifting of p basis. I take another E elements, finite many elements in K. Not necessarily lifting of p basis. You just take any finite many elements, but I impose a very weak condition, which is that the differentials of them are K linearly independent in our differential. So assume that. Similarly, we can construct a tower as right-hand side, but with respect to these generalized general elements. But we can define similarly So, and we also have the same notation if you are not confused. Okay, so we assume that we have from the delta analytic actions of gamma with coefficients k infinity. We consider this base change functor. We have W here. We assume that it can be descend to here. I mean, if we take a lifting of p basis, such descent always exists. But in general, take any general elements, we need to add such an assumption. Then, first, this Galois group is also has an open subgroup of a semi-direct product under this weak condition. So we still have a natural identification of this semi-direct product. And we can also take the standard basis here. Then for any f lies in our Faltings extension, I would like to describe what is the image. So we have phi sen f is defined explicitly by the sum of f because it is in the dual. So we x on the basis of its dual. But we add some tail twist, so we need to twist it back. It's not a problem. And this is our coefficient. And finally, we have our infinitesimal action of this standard basis to our v. So this is defined like this. So let me explain how do we prove that. The proof, as you can see, we have an explicit expression of our formula there, and I claim that it is canonical and functorial. So it suffices to prove to check if I call this formula by star. It suffices to check this formula star does not depend on the choices of v and these coordinates ti. I mean, because for any representation w, you may have a lot of descent and you can have a lot of such a system of coordinates. But in fact, we need to check the star does not depend on such a choices. How do we prove? How do we check they are independent of that? We use the variant of p-adic Simpson correspondence. Abundance over OK, developed by Suji. So that we use this to prove that, but I will not go into more details. Okay, any question? Okay, with this canonical construction of Sen operators, so that we are able to globalize in relative situation. So now we move to the relative situation. So I will change notation a little bit. So let k be a completely discrete evaluation field of mixed characteristic with perfect residue field. And I consider, for simplicity, I only consider such geometric objects. So A is a Noethering normal domain, flat over OK. But in fact, this condition is not necessary as we will impose OK. And I assume that its special fiber is non-zero. And I assume that there is a semi-stable chart of A. So I consider OK. I adjoin the indeterminates T0 to TR and TR plus 1 to TC and TC plus 1 plus or minus 1 TD to A. And it is semi-stable, so I will divide by T0 times to TR minus the uniformizer of He. So this is, and I require that the map is a. So this is a standard semi-stable chart of A. In fact, in our work, we allow more general objects than semi-stable, but let's keep it for simplicity. Notice that if I times these 1 plus d variables together, they define a strict normal crossings divisor on spec A. So that's why we call it semi-stable. And I make this notation. I take the trivial part of A, which is just the principal open subset inverting these 1 plus d divisors. And I will make a notation I will use further. So we have A here, and we have its trivial part. And because they are domains, I can consider its fraction field. I didn't by curly K. And then I consider a finite extension of K such that if I consider its integral closure of A in this fraction field, and I consider its base change to its trivial part, I assume that this is finitely done. And I consider the union of all such finite extension, and I denote it by K unramified. So I call it the maximum unramified extension with respect to this pair. And we have also the integral closure of A in this algebraic extension, and we have its trivial part. Okay. And later I will always use denote G for this Galois group. Okay. So the same in the relative situation, we proceed like this. So we consider the Faltings extension of A. So this is a canonical extension, canonical exact sequence of A bar, p-adic completion, invert P, and then give it a Tate twist. This is Galois equivariant, and I denote it by EA for the Faltings extension in the JMath. Hence the differential. But here in our semi-stable case, we need to consider the log differential over the pair KOK. This is the log differential module. So because this is exact, so we can see this is finite free over a bar hat invert P of rank 1 plus D. One may wonder how the Faltings extension is defined. So one may still may guess it we take such a Tate module, X maps to Px. We take A bar over A. There is a canonical homomorphism, but it is not isomorphism. Because we are considered a semi-stable case, we need to add some log poles. So if I only take this is not enough. It will not contain this. So we need to add some log poles. But for the experts, I would like to mention that in the existing literature, the construction of Faltings extension relies on the semi-stable chart we chose. Relies on this chart, and the construction is not canonical. But in fact, in our work, we proved that the Faltings extension can be defined canonically by the following fact. So for any S lies in A bar invert P, and I assume that it gives us a unit when we restrict to the trivial part. Then there exists a unique element, omega, lies in our Faltings extension, such that S times this omega will give us this the image of an inverse system here. So the inverse system is S, we have this power, Pn minus 1 divided by Pn, and I consider the differential here. So this is the inverse system here, and inverse system. So there exists a unique such an element here. So because of this property, we can denote omega just by the d log S divided 1 divided by n. So although A is semi-stable, and it seems that we only allow such divisors, but in fact it contains a lot of log differentials, and it remains finite free over this part. So this is quite non-trivial, and we prove it by arc descent of perfectoid algebras due to Butt and Schwarz. In fact, we don't need to really use arc descent, but we need to use the blow up, and we use the V descent. Okay, so as the left-hand side, we can also consider the dual of the Faltings extension. And we have J upper star maps to our dual of Faltings extension, and we have a canonical linear form. So our theorem, so that we can use this Faltings extension to define our to canonically define the Sen operators in the relative situation. So for any open subgroup of our maximum unramified extension, and I consider finite projective continuous representation of G with this generalized coefficient, then there exists a canonical Lie algebra action. I denoted by phi sin W. From our canonical Lie algebra of Faltings extension to it acts canonically on W, which is G equivariant. I mean, also we consider the adjoint action of G there, and functorial in W. And because we consider open subgroup, it is also functorial with respect to the inclusion morphisms of the open subgroups. And moreover, it depends only on the pair A triv and A, not on the chart. So this canonical construction allows us to do, in the future we will do globalization of them for maybe some proper p-adic varieties, and this is the theorem which enable us to do that. Okay, so let me. Yes, it's defined exactly with this by the canonical linear form. By the canonical linear form, one can associate the canonical algebra structure there. So let me mention its proof. Proof is very similar to our local field case. We need to descend V to some, we need to descend W to some V. I mean, this V should, where the Galois group should behave something like a semi-direct product of some dimple ZPs. And so that we can define explicitly how this action can be defined just as this case. Yeah, and then we prove that this explicit formula does not depend on our choice of our descent. So let me take some remarks of this descent. If G is not an open subgroup but just this case, such a descent theorem is due to G. In his p-adic Simpson correspondence for over the semi-stable pair. So he has a p-adic Simpson correspondence over the semi-stable pair. But in general, if G is just an open subgroup, and we mainly follow the argument of Tsuji to prove such a descent still exists. Yeah. And the second is to check it is independent of the choices of V and chart. How do we check the independence? In fact, we reduce to local field, because on local fields, we already established the canonical results. So let me explain how do we reduce to the local fields. So in fact, we consider prime of spec A bar, and I denote its image in spec A, and I consider the height 1 primes, and I assume that it lies over the special fiber, so that I consider all of these height 1 primes containing P, and I can consider a diagram A to A bar, and I localize at P, and above I localize at Q. So because A is a notary normal domain, so this is a DVR, and I consider its completion. And for this completion, I also consider its algebraic closure. Okay. So this is a discrete evaluation ring. So that's how we reduce to the local fields. Okay. So there is a canonical injection from A bar modulo p to the n. I consider this canonical map from the product of all of such height 1 primes Q, and I consider this algebraic closure of our discrete evaluation ring, and that modulo p to the n. This is in fact an injection because at each level it is a notary normal domain. Because at each level it is a notary normal domain, so we taking co-limits, we can have such a canonical injection. So notice that if you taking the limit of over n and we invert p, we can get something like a bar hat invert p injects to the products of complete valuation fields. So notice that our main object W is a finite projective A bar hat invert P module. So that because it is finite projective, then the canonical map, from W I can extend by scalar to define a representation here. So there is the canonical map is an injection, and we would like to define the Faltings extension acting by Lie algebra action on W, but we already established the Faltings extension, the action of Faltings extension on the local case. And because this is also finite free over this, and so that one can also obtain a canonical injection by this property. So that you see, here we have a canonical action, and by this descent, we can define a non-canonical action here, which coincides with the local field case. Because on the local field case, we allow a general system of coordinates. So one can check that you can define a non-action here which coincides with the local case. So in fact, these injections tells you that there exists a unique such action which make this diagram commute of this Faltings extension on W. So although we defined it by hand by a choice of descent, but there is only unique such one. So it has to be canonical and satisfy the functoriality. Okay. So this is our proof to reduce to the local fields to check the independence of the choice of descent. And now I make some definitions. Because this one acts naturally on W, I consider its image I called phi W. This is an image of this action inside the endomorphism of W. And I consider the image of this part by geometric of W. And I define this quotient. So we see that this phi W is canonical, and we call it is the submodule of Sen operators. And I call this the canonical submodule of geometric Sen operators. And notice here we have 1 here, and I denote its image by arithmetic, and I call its image of 1 the arithmetic Sen operator of W. Any question? Okay, so now we can discuss. We have already established the canonical construction of Sen operators. Now we can discuss its relation with Lie algebras. So let IQ be the closed subgroup, which is the image of the inertial subgroup of our local of the absolute Galois group of the local field. Then we can generalize Sen and Ohkubo's results to the relative situation. Again, we consider an open subgroup. I will mention later that why I always insist consider an open subgroup here. And if I consider a representation defined over QP, and I consider its base change so that we can define its Sen operators, then I consider the sum of all of such height 1 prime Q of this Lie algebra of these local inertial subgroups. It can be regarded as a finite dimensional QP subspace of S. This is the smallest. QP subspace such that it contains our Sen operators after extending scalars to our big coefficient ring. Okay. So now, as in Lue-Pan's lecture, we can lift the Sen operators to some universal Lie algebra. So we have a corollary that I think this curly G, I consider it is a quotient of G. I assume that it is a p-adic analytic group. Then there exists a canonical Lie subalgebras of this. And also the geometric part. It has such a property, so we consider any representation of G, curly G, with coefficients in QP, and we extend by scalars, so that we can define the Sen operators. So that we can consider the Sen operators of W, and because this Lie algebra, there is a canonical morphism because this Lie algebra will act on W through this V. This Lie algebra acts on V, and we can extend linearly to this. So there is a canonical map. And what's the image of this canonical Lie subalgebra? It's exactly the Sen operators we defined canonically. Okay. So I will not go into the proof, but let me make some remark. First, the existence of such Lie algebra and the property for V faithful is a formal consequence of our this theorem, this generalization of Sen-Ohkubo. It's a very easy corollary. This is a real corollary for this part. However, if I would like to know for any finite-dimensional V, it has such a property, then it seems that we have to follow Pan's arguments, because Pan, in his setting, he also established such a result for one-dimensional case, and we for in general we follow Pan's results or Pan's argument. So his argument, we have to use some infinite dimensional representations I will mention later. So, and the third remark is that if our dimension is V is 1, then our canonical geometric Lie algebra is generated by the canonical element defined by Pan. So this is defined by Pan. So okay. So now I have discussed the relation with Lie algebras, and finally, I will discuss our generalization of Pan's results on geometric Sen operators will annihilate locally analytic vectors. So I consider such a diagram. So we have K as the right-hand side, and I consider its finite extension, and I consider the cyclotomic extension of K prime. And then I consider another algebraic extension, I call it K tuta, which contained in our, I'm sorry, this space is too small. We have K tuta and K maximum unramified. And I assume that this G is a p-adic analytic group. I consider this setting. And I denote this part by G infinity. And I denote this by H. And yeah, and of course we have a capital G here. And we have a capital H here. I consider such a setting. Then we have our canonical, because for this p-adic Lie group, we have already picked up canonical sub-Lie algebra. So this geometric part will annihilate. Annihilates I consider this coefficient, it contains in our maximum unramified extension. And I need to take out its H invariant part so that it has the action of G. And then I take out its G infinity locally analytic vectors. The result is saying that this geometric Lie algebra will annihilate these locally analytic vectors so that we generalize Pan's result in higher dimensional case. Okay. So let me explain how we prove that. So we have our representation of curly G with coefficient in QP. And to define Sen operator, we need to extend our scalars to the above. Capital G with the coefficient, with this big coefficient. And as in Lüepan's talk, we need to consider such a, because so first, to prove such a result, we can shrink our Galois group. So this is very important. We need to, because all of such stuff is concerning with Lie algebras, so it's very natural to consider open subgroups. So that's why I always insist we consider open subgroup of this. And so that in this theorem, we can shrink our p-adic analytic group so that it become a uniform P group, so that I can make sense of this analytic function Song G. I consider this infinite dimensional representation of G. And I consider is, and I name it by S infinity. And we consider is completed base change, which is analytic functions. In fact, as we observed in the last talk, it should be like this. But however, our theories are only concerning about finite projective representations. So we need to approximate such an infinite dimensional representation by finite dimensional representations. So in fact, for this special case, we can do that. So one can take some finite dimensional representations S infinity, and S infinity is just the completion of this S infinity. So they are, and especially we can take them to be faithful representations of G. Okay, this is not very hard, but they are the finite dimensional. Okay, and we consider their base change W infinity and base change. Okay. So for each of these objects at finite level, we can define our canonical Sen operators, and because they are faithful so that that map so in this case, if V is faithful, then this is an inclusion, so that this is an isomorphism if V is faithful. So that we have a canonical identification. So this is identifies with our by G here, and we can extend by continuation. Such result also holds in general. So we can extend our Sen operators by this, so that we still have such action. Okay. So we hope that the geometric Sen operators acts trivially on this infinite dimensional representation, and I fixed by H, by the geometric part, you see, on the left-hand side. I hope that the geometric Sen operator will annihilate the H invariant part. This is somehow obvious when you consider a finite dimensional case, but it is totally non-obvious when you get such completion. And why I hope this? Because this part is closely related to the locally analytic vectors. So this is very simple, that if we prove this, then we prove this. So I think you can believe that. So we reduce to prove this claim. Ah, okay, okay. Okay, so yeah, I'm close to finish that. So recall that the definition of Sen operators relies on the descent from Wi to Vi, but the coefficients are rational coefficients. However, to see some properties of the Sen operators are preserved under continuation, we need some integral model so that we can handle this topological issue. So that in fact we need a descent of the lattice in Wi with integral coefficient. However, in general, A prime is not a nice integral model. So that the descent theory for integral coefficient representation here is not well developed. However, for A prime is dvr, this is very nice. So our strategy is, again, reduce the problem to local field by localizing at height 1 primes as before, and then finally we can use the descent of small representations, small integral representations over dvr developed by Faltings, Abes, He, and Suji, so that we can prove our statement there. So I will stop here. Thank you very much.
Thank you very much. So, thank you very much. Are there any questions? Yeah. Over? Sorry.
Just for this last theorem, I guess Pan just mentioned that he don't need really to define local analytic vectors for, I mean, he can define it generally for profinite group, right? And pro P group, I mean. So I would like to know if this annihilations, I mean, the proof still works if you just claim they annihilates all the local analytic vectors.
I'm sorry, I don't understand your question.
Yeah, I guess because in your theorem, you actually need to first take a quotient that is a p-adic analytic group and then you can do the work.
I need to take a quotient and then?
Yeah, and I mean, Pan just mentions that you don't really need to define local analytic for p-adic analytic. You can define for general pro P group, right?
Really? I don't think so. First you have an analytic group so that you can make sense of analytic functions on that. But if you do not have an analytic group, but just a profinite group, I don't know how you define the analytic vectors on that.
Maybe you just take.
He defined locally analytic representations of topological group, so it is not the locally analytic vector.
I just imagine that you can take some subnormal groups that is uniform. Okay, I guess it doesn't work. Okay.
Thank you.
Are there more questions? Yeah. Over?
So I wanted to ask to clarify what is written on the blackboard that is still there about the corollary. I didn't get exactly the state. So can you show the corollary of the theorem where you add some remarks after?
Okay, so how do I use this corollary?
Just I want to see the statement.
Okay, wait.
Can you? I don't see on the. I don't see now on the. I see the room and not the blackboard.
Okay.
Yes. So this is the board.
Ah. I want the corollary with the remark, with the three remarks.
Yes, here, this part.
Okay, so what is the statement? So you have a p-adic analytic group, which is a quotient of your
Quotient of G.
Which is related to this mix, this geometric situation with unramified Galois group. And then, what is the statement?
Okay, the statement is like this. So first we have this Lie algebra of G extended by scalars to this coefficient. And I claim that there exists two canonical Lie subalgebras.
Okay.
And then I claim it has some properties. So if I consider any representation of this curly G with coefficient in QP, finite dimensional, and I extend the scalars here so that I can define the Sen operators.
Yes.
You see the right-hand side, the Lie algebra of G acts by infinitesimal action on V, and then we can extend the scalars to an action of W.
Yes.
So that there is a natural map from this to this.
Yes.
And I would like to describe what's the image of our canonical Lie subalgebras I just defined.
And
the image is exactly the Sen operators of W we just defined.
Is it also the case for all? Why do you need the W comes from V? Is it also true when W is just a semi-linear representation of?
If W is just a semi-linear representation, yeah, it look. Yeah, because our previous generalization of Sen and Ohkubo's theorem only discussed the relation of representation comes from QP. If the representation comes from QP, then the Sen operators essentially capture the actions of some inertial subgroups. So that's only for representation with the coefficient in QP. By the theorem of Sen and Ohkubo, we can have the relation with the Lie algebras of inertial subgroups. So only for this, I have the relation with the Lie algebras.
Yeah. So maybe you continue the discussion. So
yeah, I'm sorry.
Okay. So thank you very much.
Yeah.